In this video, I'm going to go over how to graph a piecewise function when you know the equation. We'll start with this first function, g of x, and I'm going to start by looking at the domain restrictions. The domain restrictions here tell us that a part of the graph is going to show up where the x values are greater than or equal to -2, and the second part of the function is going to show up when x is less than -2. So I'm going to start by just marking a dashed line. Make sure that it's dashed on that boundary between the two halves of the graph so that I don't get confused. And then I'm going to change my color, and I'm going to work on graphing this first piece right here for the part that is greater than or equal to -2. And to do that, I'm going to think about point slope form. Point slope form is y equals m times x minus x1 plus y1. So I'm thinking about a locator point, and I'm thinking about the slope. So the locator point is always the x1 and the y1. The slope is always the m. The locator point that I see looking at this function rule is -2, -4. And if you'll notice, on this particular piecewise function, the locator point is the same whether I'm looking at the top function rule or the bottom function rule. So I'm going to come over here, and for this piece it's greater than or equal to -2, so I know I'm thinking about a solid dot. I'm going to put a solid dot on -2, -4 as best I can. My accuracy may not be very good with this, so you'll have to make sure you're paying close attention. And then I know that my slope here is 3, so if I'm thinking about a slope of 3, I'm thinking about rise over run. The rise would be up 3, the run would be over 1 to the right. So I'm going to plot some more points, remembering again that I'm looking at the values greater than or equal to 2. So I'm looking for this half of the graph first. So if I go up 1 over 3, I'm going to have a point right about here. I'm going to go up 3 over 1, right about here. Up 3 over 1. Up 3 over 1. And because there's no other boundary that tells me I'm going to stop, I'm going to connect my dots, preferably using a straight edge on your paper. And I know it's going to go on forever because it's anything that's greater than or equal to -2, so I'm going to put an arrow. When I do the second half here, I'm still looking at the same locator point, but this time my slope is -3. And so most of us are accustomed to thinking about rise over run as the rise is either going up or down, and the run we kind of tend to always think about going to the right. The only problem here is if I do that process, I'm going to wind up counting. So if I start at my locator point, I'm going to wind up counting down 3 over 1 to the right, down 3 over 1 to the right, and I'm going to wind up with a piece of the graph that's over here. The problem with that is my function tells me that now I'm looking at the left-hand side of this dashed line. So I really need to see the part of the line that shows up over here. So in order to do that, I'm just going to kind of rethink slope. And I still want it to be -3, but if I change the sign, if I change it to +3, sorry, that's a little messy, over -1, now I would be thinking about going up 3 and over 1 to the left. And because I would have one negative, I'm actually going to erase this and make it a little clearer for you. So if I think about, I just moved my paper a tiny bit. If I think about making it +3 over -1, I still have one negative and one positive, so I'm still doing a slope of -3, but this time I can count up 3. So I'll start at this locator point, count up 1, 2, 3 over 1 to the left, 1, 2, 3 over 1 to the left, up 1, 2, 3 over 1 to the left, and so forth. I can connect my dots, make an arrow, and see when I do that counting and change the sign of the rise over the run but keep it negative, I still have a negative slope, which is what I was expecting from this. It still is going down or decreasing when I trace it from left to right, but it's easier to count and figure out what it should be. One final word here before we move on to the next one. This is x is less than -2. So that would indicate that the locator point would have an open circle here. But that open circle has already been colored in by the blue half of the function, so I don't really need to worry about that. When we reflect on this question, what do you notice about this graph? I heard lots of you coming up with the correct answer in class, or one good noticing that's going to help you later. And that's that even though it's written in kind of a way that I don't recognize, when I see the shape of this, I notice that it's also an absolute value function. So even though I'm used to absolute value functions having the equation with absolute value in it, we can actually write absolute value as a piecewise function, and we'll be practicing doing that in Unit 2. Okay, at this point I'm going to move on and show you this other one. So you'll have another example to look at. I'm going to start again with my domain restrictions. First, I'm going to look at this one that says that x has to be in between 6 and 10. We're not going to include 6, so we'll have an open dot somewhere around with an x value of 6 and a closed dot around 10. So I'm going to count over 1, 2, 3, 4, 5, 6, and I'm going to mark my dashed line. And I'm going to count over to 10. I'm going to mark my second dashed line. So I know that this function needs to appear in between these two lines and nowhere else on the graph. And this is where I want to start thinking about different ways that I can graph functions using all of the strategies in my toolbox instead of relying on just one. Most of us are probably tempted at this point to plop down the y-intercept of 4 and start using the slope of 1 over 3, or rise over run of 1 over 3, to plot my points. The only problem with that is when I use a y-intercept of 4, I'm already going to have a point here that's outside of where my function needs to happen. So instead, what I'm going to do is use a process chart for this one. So I'm going to be thinking about an XY table with a process chart, and I'm going to choose the values based on the domain restrictions that come from right here. So if I substitute a 6 in for x, I'm thinking to myself 1/3 times 6. This is moving. I don't want it to move. Not sure. Okay, I think we're good. 1/3 times 6. We've got a little random mark there. Plus 4. 1/3 of 6 is 2. 2 plus 4 is 6. So I know I'm going to have a dot on the point 6, 6. 1, 2, 3, 4, 5, 6. And I know it's going to be open because this symbol right here tells me that. To move on to the next one, let me try and erase this. It's not letting me. I don't want to do that. Sorry for that. To move on to the next point, I could plug in 7. The only problem with substituting 7 in is that I know 7 over 3 is going to give me an answer that's not a whole number, so it's going to be harder for me to graph. So I'm actually going to move on and think about what would be easy to graph. If I substitute 8 in, 8 over 3 is still not a whole number, so I'm going to skip this one and this one for now till I come to something that's a little more friendly. If I substitute 9 in, 1/3 of 9 is 3. So I'm using this function rule to evaluate. 1/3 of 9 is 3. 3 plus 4 is 7. So I know I'm going to have the point 9, 7 on my graph. 1, 2, 3, 4, 5, 6, 7. And that's the same thing that I would get if I used this initial point and counted up 1 over 3 the way my slope does. I can connect it and estimate where it's going to end there on 10, put a closed dot, and that's going to give me the first piece of my graph that I need to do. To do the second one, so I'm just going to do a little bit more and then I'm going to give you the answer. To do the second one, again, I'm starting from the domain restriction, so I know I'm going to look at in between 0 and 4. This is where my graph needs to show up. this equation's written in point slope form. Okay, so I'm looking at this function rule. My locator point for this one is 1, 3. So I'm going to go to the point 1, 3. And that point is in between my two dashed lines, so I can go ahead and put it on the graph without any trouble. And then I'm going to use the slope. It's a negative slope, so I can go down 1 over 1 to create a negative slope. And I'm going to make sure to put an open dot because of this part. And I can also go up 1 over 1 to the left. That's also going to be an open dot because of this part. I can connect those two endpoints, and that's going to give me the second piece of the function. From here, I'm going to stop the recording, and I'm just going to put the answer on there so that you can see this third part. If you have questions, just let me know. Okay, so I put the last piece on here. I did not intend to make it go off the grid. That was an accident. This top point would be the point -620. So your graph would look something like this.